Hello and welcome to this video tutorial on RxGaming. I am Bartl-Geller. I am a research scientist in the Forest Resilience Lab at the University of Washington, and I am the lead developer for the RxGaming tool. And in this video, I'm going to demonstrate how to use the RxGaming tool and some of its features. I'm going to go over some of the data and processing pipelines, as well as some of the outputs and general workflow with the tool. When you install the tool, and you extract the files, you'll be greeted with a folder that looks like this. The first thing to note is the README document, which will tell you the version of RxGaming that you are using and where you can find the manual. If you follow this link, it'll take you to a Google Doc, which has a manual for the tool with extensive resources about how to use the tool, the ideology behind using the tool and the way the tool was developed, the different processing workflows and the different features in the tool. If you have any questions, it is very likely that you'll be able to find the answers to these questions in this document. So the first thing you need when using the RxGaming tool is some LiDAR data, and this data has to be processed into tree approximate objects in a way that is appropriate for use in the tool. There are three primary processing workflows that the tool is designed to work with. The first is to use this R script that will process the data through the LiDAR R package. You can also process the data through Fusion, which is the U.S. Forest Service's LiDAR processing package. And the last option is Lapis, which is a processing package that was developed in the Forest Resilience Lab and is publicly available but not widely adopted. But it creates metrics analogous to Fusion, and so they can be used interchangeably. If you would like to use Fusion or Lapis, I would direct you to the RxGaming manual, which will then direct you to the documentation for those particular tools themselves. If you want to process the raw point data through the LiDAR script, you'll double click on this, and if you have RStudio installed, it will open in RStudio, which is the recommended processing tool. You'll run this script. First, you'll edit these parameters above this line, and then you will run the entire script, and the script will create data for RxGaming for you. This line here is the file folder where you have the point data in LAS or LAZ format. This file here will be your shape file that has your treatment units. This attribute here is going to be the column name from the attribute table in the shapefile that delineates the unique identifier for each unit in your shapefile. This folder here is going to be where the outputs will be written, and this folder will be created for you if it's not already created. And then this parameter is to set whether or not the vertical units of the point data are in feet or in meters. Because we cannot disambiguate the units from the metadata directly, the user has to input this. Most commonly, it's in meters, but if you know that it's in feet, which are some unusual acquisitions are, you can specify that here. You don't need to modify anything below this line, and this script will install the required packages and process the data and create outputs for you. Those outputs look like this. You'll have a folder for your canopy height models, and there will be one canopy height model per treatment unit in the shapefile. This folder will be the clips of the point data from the larger data set that you supplied. And the first number here will be the unique identifier for each treatment unit, and then there will be 9 clips in total with a small shift on the points in each file. You can more or less ignore this, and I recommend if you want to use the LiDAR data directly, just use the 0, 0 points. Those are going to be what were delivered, and then these other files are basically accounting for imprecision in the LiDAR data when creating the canopy height models. This folder will have a layout. This file is going to be is more or less going to be the same as the input shapefile with the units. It's just restructured in a way to connect the rasters to the different units for processing in RxGaming. This folder will have a mask layer for each unit and then a merged layer that masks the entire project area. And then this folder will have information about your segments. So the first time you process, you're going to just have a segments folder or segments file, which will be the individual canopy segmented into different individual trees, TAOs, tree approximate objects, and the other file will be the tops file, which identifies the high point within each subdivided region in the canopy. When you process the data through RxGaming, it will create two additional files, the MHM, which is the max height model, and a CSV that is all the same data, just in tabular format. In order to run this file, after you set your parameters, you can click source, which will run the entire document, or you can press Control plus Alt plus R, and that is the same as clicking source, which will run the entire document. Let's explore some of the data. This is the sample units file that we processed through the LiDAR script. I just copied it in here for distribution if you're following along using the same sample data. What you see here is a shapefile with different polygons representing different treatment units that we're interested in processing through RxGaming, and there's various data in the attribute table. This poly name is our unique identifier. And so if we look at the layout from the script that we processed, you'll see that the polygons are the same, but looking at the attribute table is much simpler. It's just a unique ID. And that poly name has been renamed to unique ID, which is what the RxGaming tool expects. Now we can look at, for example, a canopy height model for one of these treatment units. Will look something like this. In this symbology, green represents closer to the ground and red is higher to the treetops. And we can also look at some segments. Each segment will have a unique identifier, so the appropriate symbology for this will be unique values. And you can see here each tree approximate object has its own color and its unique ID for each basin. And finally, we can look at the tops layer, which will identify a pixel in each region to be the high point for that region. Looking at the data processed through Fusion or Lapis, it's very similar. You'll have similarly a folder for the canopy surface model and the tree approximate objects, as well as the layout. And similarly, we'll have similar folders, canopy height model, segments, or tree approximate objects, and a layout. If you want more information about this, see the manual. All right, so we have our data processed and ready to use RxGaming. So let's get started with that. So first, to open the RxGaming tool, we'll double click on rxgaming.exe in this folder. This black window will open up. This is the dev and debugging window, and for most uses, we don't have to look at it. It's going to stream a lot of debugging information at the start, and we just let that run. We don't need to pay attention to this. After a few seconds, that pre-processing will complete, and we'll have this first window for RxGaming open up, where it's prompting us if we'd like to work from a save file or start a new project. In this tutorial, we'll work from a new project starting from the first time. So we'll click Start a New Project. That opens up this page, which is the project settings page. First setting for your project is going to be the name. This is purely cosmetic. It will show up in the outputs and in the user interface when we're using the tool. So we'll call this sample data. The next line is the treatment unit polygon file. That's going to be the same file that we supplied earlier as the treatment unit. So if you're following along, it'll be the sample units file in the sample data. If you're using the LiDAR script to process your data, you must provide the exact same file that you provided to that script, as we only process LiDAR data inside the treatment units in that script. This has the advantage of creating smaller data sets that are easier to transport, but if you try to run a different treatment area, the program will give you an error saying that the treatment unit polygon does not overlap your data. However, if you use Lapis or Fusion, which process larger areas, it will be easier to use different treatment units in different areas without reprocessing. The next file folder is the LiDAR data root folder. And in this case, we're going to use the sample data folder that we created with the LiDAR script. If you're using the Fusion or Lapis folders, you'll supply the root folder for the Fusion or Lapis runs. Since we're using the LiDAR folder and the sample data that came with the tool, we're going to give it the sample data folder. The next line is the reference data table. This is an optional table that has reference information about your treatment area. This is going to be a CSV. If you're interested in learning more about the type of data, see the manual. In this case, we're going to use the sample reference data that came with the sample data. However, if you do not have reference data, you can leave this line blank. Next is the name field that we want to use as the unique identifier. We're going to use the poly name field that we had the same field we used when we just delineated unique ID in the LiDAR script. This is case sensitive, so you need to spell it exactly the same as it is in the file. And you can leave it blank if you don't have a unique identifier. However, then you'll just have no name for each of your treatment units, and it will be harder to distinguish them. I need to make a minor correction that I should say poly name with a capital N here. The next attribute is the number of threads to process on. If you increase this, the initial processing for the tool will go faster because it can distribute the load across different processing threads, but it will use more of your computer resources. We recommend that you leave at least 25% of your threads available for other computer use while processing. In order to determine the number of threads on your computer, you can hold Control, Shift, and Escape to open up the Task Manager. Then you click on Performance, and then you click on CPU. The number of cores will be listed under Cores. This is the same as threads. And you want to leave at least 25% free. So we would only use 12 as our max. This is not a very large area, so we'll use even fewer, and we'll say 8. The last thing is whether or not you would like to autosave. If you're processing a large area, for example, 50 units, you might want to leave that processing overnight, in which case it would be helpful to have it automatically save that processing when it completes in case your computer turns off or restarts. If you like to autosave, you check the autosave box, and then you'll specify a save location. Now we can save our settings. We click Save Setting As if we want to save a new file. If we've saved our file, we can then click Work from Saved File instead. Navigate to our saved file. And then it'll open. Now, if we change some settings, for example, reducing the number of threads to 6, or if we changed our reference data, or we are processing over a different LiDAR data or treatment unit polygon, we can click Save Settings, and we will update the saved settings for next time we open the settings. Now we're ready to process. So we'll click Start, and processing will begin. There will be abbreviated processing information in this dialog box at the bottom of the project settings pane, which will tell us approximately where it is. and there'll be in-depth processing information in the development window. Once you click start, the program will process, and depending on the size of your area, it could take a while. So we will come back once this finishes processing. Eventually, the tool will start processing the individual treatment units, and you can see that it is processing them here. We've got 10 treatment units, and these are the different threads that are processing. When it completes processing, then the RxGaming gaming window will show up. Once RxGaming finishes processing, you'll be shown a window looking like this, or exactly like this if you used the same sample data that we're using in this tutorial. There are two tabs, the stand tab and the landscape view tab, and we're going to start with the stand view tab. On the left, you'll see all your units, and if you click on the different units, it'll display the different units in your data set. On the bottom left, it shows the density, basal area, mean clump size, and canopy cover of the current condition of the stand. And then when we talk about treatment, this is where we'll be setting our targets for each of those things. In the middle, we're looking at the canopy height model for the stand, where blue is closer to the ground and red is closer to the tops of the trees. On the landscape view tab, we're going to see these different, all our treatment units displayed as blue triangles, and then the reference data is going to be shown as the orange gradations behind them, where darker orange means there's a higher density of reference sites that exhibit that condition, and lighter orange means fewer reference sites exhibit that condition. Each graph is going to have density on the x-axis, and then basal area, mean clump size, and canopy cover on the y-axis. When you hover over a triangle, it's going to show you a polygon. The polygon represents a simulated change in condition for that stand. What this means is we process removing trees in a variety of different ways and measuring structure at each of those intervals. This uses a diameter limit of 30 inches, and so it depending on the parameters on your particular site, these are not necessarily super accurate, but it gives you a general idea of what kind of structures can be created and gives you information about how those structures overlap with the reference condition. For example, in this one, the orange polygon is the area that can be created in the treatment of the stand, and the blue polygon is where the treatments in the stand overlap with the reference condition. If you click on the stand, it'll take you to that stand, select it, and select it in the stand view. So we can use that to inform our decisions about alteration of structure. For example, stand 19 here looks like it is on the high end of basal area for the reference sites, and we have a strong zone of basal area around 100 square feet per acre and around 200 square feet per acre. So somewhere in that range would be appropriate for these stands. So this one is a small stand, so we're seeing a very high basal area, but it's perhaps only because it's quite small. But we can target 150 basal area, residual basal area, and click Show Treatment to simulate the treatment of the stand. Now, the stand is not very large, so we aren't going to be starting to see those patterns. But on a larger stand, when we alter the structure, we'll start to see emergent patterns created. If we click on the arrows, we can look at the basal area distribution of the individual trees before treatment and after treatment, as well as the clump size distribution before treatment and after treatment. We also will see the reports for current structure, post-treatment structure, and then the targets that we selected. And finally, on the last page, we'll see information about the basal area of the trees that is removed. So we removed 60 square feet per acre of basal area, and the trees had a range from very small to 5 square feet. We can change our diameter limit using this slider, and that will change the maximum size tree that can be removed by the treatment algorithm. And we can change our view mode to look at individual basins or clumps for the pretreatment and post-treatment condition. On the landscape page, we can see how the current condition, the target condition, and the treated condition interact. In this example, we did not set target for the density, but we did set target for the basal area, and that is represented with the green square. And then while we did not target a removal of density, in order to remove basal area, we had to reduce the density, and you can see that reflected in the magenta circle. The line connecting the three symbols allows us to see which stand which stand we're modifying. If I want to export the data from a treatment, I go to File, Export, and we can export raster data, which will be the displayed canopy height model, shapefile data, which will be a point file of the high points, a geotiff, which will be a georeferenced image that is exactly like what we're seeing on the screen, and the tree list, which will be a CSV of the information about the TAOs. If we're displaying a treatment, it'll export information about the treatment, and if we're not displaying a treatment, it'll export information about the untreated stand. So for example, if we want to export a geotiff, we enter our file name and save, and that geotiff can now be loaded into ArcMap. Like so. This is especially useful because you can load this map into Avenza or PDF maps, and you will be able to compare the results from the tool to your observations in the field. If we want to save our work, we go to File Save or File Save As, and you'll also be prompted if you'd like to save your work when you close the program. Now in the future, we can load that saved file that we saved directly and skip the processing stage. This has been a short demo introducing how to use RxGaming tool. We refer you to the manual for in-depth details, and you'll be able to contact the developer using information provided in the manual. Thank you for your interest in RxGaming, and we hope that this tool can help you in planning your project areas, designing treatments around clumping patterns, and making the use of LiDAR data more easy and accessible in your projects.